everyone. Welcome back to the Incredible India podcast series. I'm Sam.
I'm Taylor.
So imagine you're staring at the foundational computer code that, runs your smartphone.
Right.
The logic behind the search engine you use every single day, the whole architecture of the modern internet.
Yeah, the stuff we just totally take for granted.
Exactly. Now imagine realizing that this exact mathematical structure wasn't invented in like a 1950s tech lab. It was actually built by a scholar holding a palm leaf 2,500 years ago.
Sounds completely made up.
It really does. But today's deep dive is built on some absolutely mind-bending sources provided by Five Senses Tours. And our mission today is to explore how an ancient thinker essentially wrote the world's first source code completely without a computer.
Yeah.
And why the people building cutting-edge artificial intelligence today are frantically studying his work.
Because if you're listening right now, the connection between an ancient manuscript and your modern smartphone, it probably seems like a massive leap.
Oh, totally.
But the reality is that the foundational problem of how to give perfect, unambiguous instructions, whether you're talking to a silicon microchip or, another human being that was actually solved millennia ago near the banks of the Indus River.
It's just wild. And to really grasp how big of a historical curveball this is, we actually need to start our deep dive in the modern era.
Okay, let's go.
Let's travel back to 1959. So, dawn of the computer revolution, you have these massive, room-sized mainframe computers.
Right, the ones that took up entire floors of buildings.
Exactly. And computer scientists are staring down a huge problem. They need a reliable way to talk to these machines.
Because early computers possessed literally zero intuition.
Nothing.
They couldn't understand the messiness of human language at all. They needed a highly structured, very mathematical way of receiving instructions. So in 1959, two computer scientists named John Backus and Peter Naur, they invented this specific notation system to describe the syntax of programming languages.
And at the time, they were just trying to build the framework for an early language called ALGOL 60.
Right, exactly.
But this notation system they invented becomes known as Backus Naur Form. And looking through our sources, it becomes super clear that this isn't just some footnote in tech history.
Oh, not at all.
This notation is basically the grandparent of Python, JavaScript, C++I, like all modern computer code.
It's the bedrock.
Right. It gave scientists the structural toolkit to tell machines exactly what to do.
And Backus and Naur were rightly celebrated for this. I mean, it was a massive breakthrough that fundamentally changed computing.
Sure.
But fast forward just a few years to 1967.
Okay.
A researcher named P.Z. Ingerman publishes a letter in the Communications of the ACM.
And for context, for anyone listening, the ACM is the absolute gold standard. It's the most rigorous computer science journal in the world.
Yeah, you don't just publish fluff there.
Yeah.
And Ingerman drops a total bombshell in this letter.
Oh, it's huge.
He points out that this revolutionary Backus Naur form, this bedrock of modern computer science we just talked about, had actually already been invented. Except it was invented 25 centuries earlier to describe the Sanskrit language.
It's crazy.
Ingerman even proposed in his letter that the entire computing world should rename their foundational notation to the Panini Backus form.
Okay, wait, I have to stop you there because I have to admit I had some genuine skepticism when I first read that in our research.
Sure, yeah.
How could ancient linguistic rules, which were meant for humans speaking out loud, possibly be structurally equivalent to modern computer syntax designed for silicon
It
chips?
sounds like a stretch.
It does. It sounds like we're just, finding shapes in the clouds, making a poetic comparison rather than a scientific one.
Well, and that skepticism makes complete sense.
Yeah.
It totally sounds like a stretch until you look at the concept of formal language theory.
Okay, break that down for me.
So, defining a syntax for a formal language requires absolute, uncompromising mechanical precision. It doesn't matter if you're giving instructions to a microchip to process data, or if you're trying to map out the exact phonetic output of a human mouth. A formal language is defined entirely by a finite set of strict rules.
So you mean there is absolutely no room for, you know what I mean?
None whatsoever. Zero human judgment, no intuition, no interpretation based on body language or context. The rules just have to be applied mechanically to determine if a string of symbols is valid or invalid.
Wow.
So Backus and Naur built a formal language to instruct a machine. The ancient scholar Ingerman was referencing built a formal language to describe Sanskrit.
The end goals were completely different.
Exactly. But the mathematical toolkit required to solve them with zero ambiguity. It was completely identical.
Man, if this exact mathematical toolkit was required to talk to machines in 1959, who on Earth was utilizing this level of mechanical precision 25 centuries before the microchip even existed?
Right. Well, that brings us to the scholar himself. His name was Panini.
Panini. And he lived roughly between 400 BC and 200 BC, right?
Yeah, in a town called Shalachula, which is located near the Indus River in present-day Pakistan.
So what did he actually build?
What Panini built was a text called the Ashtadhyayi, which literally translates to 8 chapters. And inside these 8 chapters, he laid out roughly 4,000 sutras, or rules.
4,000.
Yeah, and these 4,000 rules do something just staggering. They completely mathematically define the Sanskrit language.
See, I want to make sure we visualize just how revolutionary this approach is. Because it's not like reading a dictionary, right?
Yeah, not at all.
Just think of it more like a chemical formula. Like when you study chemistry, you don't memorize every possible combination of molecules in the universe.
Right, that would be impossible.
You'd never finish. Instead, you learn the strict laws of chemistry, how certain atoms bond under certain conditions.
Yeah.
And from those finite laws, you can generate an infinite number of valid chemical compounds.
Exactly.
Panini basically did that for human language.
Yeah, and that generative concept is the absolute core of his genius. Like, think about English. English is notoriously chaotic.
Oh, it's a mess.
When you learn it, you just have to memorize thousands of irregular verbs and bizarre spelling exceptions.
Right.
It relies on precedent and habit.
Right.
Panini didn't write down a list of correct Sanskrit sentences to memorize. He wrote a generative engine.
So you apply his 4,000 rules in a specific mechanical order, and if you follow the rules, you generate any grammatically correct sentence the language permits, and you mathematically exclude every single sentence it does not.
That's it perfectly. And when computer scientists look at the Ashtadhyayi, they immediately recognize source code.
They see it right away.
Yeah, it's a system where syntax is generated from a finite set of rules, which perfectly fits the definition of a context-sensitive, formal model of language.
Which basically just means the rules adapt based on the context of the elements, but they do so in a strictly mathematical way.
Exactly. And he did this entirely in his head and on palm leaf manuscripts, centuries before anyone in the 19th or 20th century started developing mathematical logic.
It is honestly blowing my mind. We really need to dig into the actual architecture of this ancient code because the mechanics are where the genius really shines.
Oh, absolutely.
Like, how do you compress an entire living, breathing human language into just 4,000 rules?
It's a huge compression problem.
Yeah. According to our sources, Panini started by stripping the language down to about 1,700 basic elements, things like raw phonetic roots, nouns, verbs, vowels, and consonants.
Right.
He gathered all these raw materials and he put them into distinct classes.
And the algorithmic compression really happens with how he labeled those classes. Once he grouped the raw elements, he assigned them single letter or syllable codes.
Okay.
In Sanskrit grammar, these highly compressed indicator codes are called anubandhas.
Wait, okay, I'm trying to visualize this workflow. He groups a massive category of words and then assigns a single arbitrary placeholder tag to represent that entire group. Is that basically what modern programmers do when they create a variable in a language like Python?
That is exactly the mechanism. A modern programmer doesn't write a brand new custom function for every single piece of data.
That would take forever.
It would be incredibly inefficient. They write a function that operates on a variable, which acts as a placeholder representing an entire category of data.
Wow.
Panini engineered the exact same efficiency. If one of his rules referenced a specific anubandha, that rule automatically and instantly applied to every single phonetic element inside that variable's class.
But it goes beyond just variables too, right? Because Panini also created something called paribhashas.
Yes.
These are meta rules, literally rules about rules. And to understand why this is so critical, think about how a modern computer compiler works. If you feed a program conflicting instructions, say, Rule A tells a computer to do one thing, but Rule B tells it to do the exact opposite, the compiler doesn't know what to do.
It crashes.
Exactly. You get the blue screen of death.
Right. And a system of 4,000 interlocking rules is bound to have overlaps and conflicts. Panini knew this.
He had to.
So he built a higher-order logic to prevent the linguistic engine from crashing. He wrote specific meta-rules that basically act as traffic cops.
Like what?
Well, for instance, he created a strict meta-rule stating that if two rules contradict each other during a transformation, the rule that appears later in the physical text of the Ashtadhyayi always overrides the earlier one.
He literally solved the blue screen of death for spoken language.
He really did.
It's incredible. And our sources provide a really concrete example to make this tangible. Let's look at Panini's rule 6.1.77.
Okay, Rule 6.1.77.
Yeah. This rule dictates that if certain vowels are followed by a dissimilar vowel, they are automatically replaced by corresponding semivowels.
Okay.
So you take the word eti, which means end, and you combine it with the word adi, which means beginning.
Yeah.
You feed those two raw elements into the engine.
And according to Rule 6.1.77, the engine mechanically processes the vowels and produces the combined word eat yadi.
Just like that.
The transformation happens without any human thought required.
Yeah.
It's completely deterministic.
Yes. Deterministic meaning zero ambiguity. The rules dictate only one mathematically predictable outcome every single time.
Right.
It is pure linguistic engineering. Two human minds, separated by 25 centuries, John Backus in 1959 and Panini around 400 BC, looked at the identical underlying problem of describing syntax with mechanical precision and arrived at structurally equivalent solutions.
Which brings us to the most urgent part of our deep dive. Because Panini isn't just some ancient curiosity relegated to history departments.
Right.
He is an active, heavily researched subject in modern artificial intelligence labs today.
Which I get why a linguist or a historian cares about this. But why are modern AI engineers, the people actively building the next generation of large language models like ChatGPT, why are they digging through 2,500-year-old Sanskrit texts right now?
It comes down to how large language models actually process information, and really the massive computational cost of dealing with messy languages.
Okay.
Currently, models are trained heavily on languages like English, but English relies entirely on word order and context.
Yeah, that makes sense.
Think about the word bark. If an AI reads the sentence, "the dog's bark was loud," versus "the tree's bark was rough," it has to analyze all the surrounding words just to guess the meaning.
And that guesswork takes an enormous amount of computational power.
Huge amounts.
The AI has to learn those chaotic patterns through sheer brute force, looking at millions of parameters just to figure out what a noun is doing in a specific sentence.
Exactly. But Sanskrit, specifically because it was structured and fixed by Panini's rigid rules, operates entirely differently. Researchers are finding that Sanskrit is incredibly token efficient for AI models. It encodes syntactic and semantic information through deterministic morphology rather than relying on loose word order.
Okay, let's translate that phrase deterministic morphology because I feel like it's the key to the whole AI connection.
Yeah, let's do it.
So morphology is just the study of how words are built. And deterministic, like we mentioned, means it follows strict mathematical rules with a single outcome. So instead of English, where a word's function floats around depending on the sentence structure, Panini's word-building rules result in exactly one unambiguous meaning embedded right into the structure of the word itself.
And when the rules are mathematically baked into the structure of the words like that, an AI model doesn't have to waste processing power guessing based on word order.
Oh, wow.
It doesn't have to memorize a billion chaotic English sentence patterns. It just has to learn Panini's strict generative rules.
That's so much cleaner.
Right. By learning that clean algorithmic math, an AI model can theoretically achieve much higher accuracy using far fewer parameters.
And it's not just theory. The sources highlight that researchers at the Indian Institute of Technology, Delhi, as well as Jodhpur University in Kolkata, have literally taken Panini's ancient sutras and codified them directly into computer programs.
Yeah.
They are using his rules to build modern natural language processing systems. And they are seeing astonishing results, like achieving 98% accuracy and automatically deriving grammatical roots in Bengali.
They're directly applying an ancient palm leaf text as a modern machine algorithm.
It's just wild.
The exact 8 chapters Panini composed near the Indus River are actively parsing modern languages for artificial neural networks today.
Man.
When computer scientists look for maximum computational efficiency, they want the cleanest, most logical rule set available. Panini provided exactly that.
It really makes you wonder what kind of world produces a mind capable of building a linguistic compiler from scratch?
Yeah.
Because Panini didn't just emerge from a vacuum. Our sources detail that he was part of this staggering intellectual environment, likely teaching at the ancient University of Taxila.
Oh, Taxila was far more than just a school. It was an ancient incubator for systematic thought.
Yeah.
It was situated right at the crossroads of the main trade routes of Asia, so it drew students and scholars from Greece, Arabia, China, and Babylonia.
A real melting pot.
Completely. And they fostered a culture of uncompromising rigor, teaching the Vedas, advanced mathematics, medicine, astrology, military strategy.
The concentration of intellectual breakthroughs happening in this one geographic hotspot is just miraculous. I mean, it wasn't just Panini.
Right.
The University of Taxila simultaneously produced Panini, who gave the world formal grammar theory, Chanakya, the master political strategist who engineered the Mauryan Empire, and Charaka, the father of systematic Ayurvedic medicine.
It's like an ancient Ivy League and Silicon Valley combined. And that density of genius was really possible because of an obsessive culture of debate and knowledge preservation. And Panini's work was the ultimate catalyst for that preservation.
How so?
Well, by fixing the grammar of Sanskrit so perfectly, Panini created a stable, unchanging foundation for thousands of years of subsequent Indian scholarship.
Because the language wasn't constantly shifting and mutating and changing definitions the way English does century by century.
Exactly.
Scientific ideas could be recorded with absolute precision.
Right. Because of Panini's rigid code, subsequent giants of Indian science, like Aryabhata and Brahmagupta in mathematics, or Sushruta in medicine, they could write texts that remained perfectly intelligible to scholars 2.5 millennia later.
Wow.
They didn't have to worry about their words losing their meaning over time.
And that tradition of intense structural inquiry extended far beyond Taxila, really permeating the broader landscape of ancient Indian science.
Oh, absolutely.
We see figures like Canada in Gujarat, who proposed a highly structured atomic theory of matter 2,600 years before John Dalton, or the mathematicians of Karnataka, who were describing the infinite series and principles of calculus a full 5 centuries before Isaac Newton was even born.
It completely reframes how we view the timeline of global science.
It really does.
We often carry this subconscious bias that formal logic, structural mechanics, and algorithmic thinking were all born during the European Enlightenment or, the mid-20th century computing boom.
Right.
But the reality is that the foundation of formal structural techniques, things like meta rules, recursive transformations, and symbolic classification, those were being utilized at the highest levels millennia ago.
We do have to be clear about the history, though. Panini didn't sit down and write instructions for a machine.
No, of course not.
He didn't invent computer programming in the literal modern sense of building software. His goal was solving the profound problem of describing a living, breathing human language with total uncompromising rigor.
Right.
But the masterpiece of human logic he invented to achieve that rigor, this toolkit of variables, classes, and meta rules, it turned out to be the exact same toolkit that computer scientists needed 25 centuries later to talk to microchips.
It really serves as a powerful reminder that the urge to organize information, to decode the underlying mechanics of the universe, and to build elegant systems of logic is a deeply ancient and universal human pursuit.
Well said. Before we wrap up this deep dive into ancient algorithms and modern AI, there is something we need to pass along to you. If you decide to travel to India, we have a recommendation. 5 Senses Tours organizes tours across India which are immersive cultural experiences. You can email contact@5sensetours.com. Note 5 is written as a numeral in contact at 5sensestours.com. Or WhatsApp to +919 845 677 446.
I think the most fascinating thing to take away from our dive into Panini's work is a profound question about human cognition.
Yeah.
If human beings were capable of designing a perfectly mechanical, computer-like syntax for spoken language millennia before the very first microchip ever existed, does that mean the logical architecture of computer programming isn't actually a modern invention at all, but rather a fundamental hardwired feature of the human mind just waiting to be uncovered?